28 sharks. Caught off the coast of Rio de Janeiro, every single one tested positive for cocaine. Not trace amounts, not a statistical fluke. Levels high enough that, in a human, they would register on a drug test. These are apex predators, animals older than trees, and their blood now contains traces of a drug flushed down a toilet in South America. This is marine biology. You're watching Curious Minds. Let's begin. Here's what we're going to prove in the next 30 minutes. First, the cocaine in those sharks was not an accident. It arrived through a pipeline nobody planned to build, but everybody contributes to. Second, sharks are not the only animals carrying our pharmacy in their blood. Meth-addicted fish exist. Antidepressant shrimp exist. Prozac-altered oysters exist. Third, this chain does not stop at the ocean floor. Every step it takes moves closer to a human dinner plate. The headline is funny. What's underneath it is not. The study that started this was published in 2024. A team at the Oswaldo Cruz Foundation in Brazil. Their question was simple. We know pharmaceuticals leak into rivers. We know those rivers reach the coast. But does anything actually hold on to them? So they picked one of the most common animals in that ecosystem, the Brazilian sharpnose shark. Coastal, abundant, caught regularly in local fisheries. Exactly the kind of fish that could end up on a plate. They collected 28 of them. Then they started running tests. The results were not what they expected. The process was straightforward. Muscle tissue and liver samples from each shark run through a mass spectrometer, screen for over 100 compounds, pharmaceuticals, stimulants, illegal drugs, and their chemical breakdown products. This is the same technology used in human forensic labs, the same tech that catches athletes doping at the Olympics. The team wasn't hunting for cocaine specifically. They were running a broad sweep. Nobody had ever done this on sharks in a coastal ecosystem this exposed to urban runoff. They were expecting to find something. They were not expecting to find everything. Every single shark came back positive for cocaine. Not half, not most, all 28. The concentrations in muscle tissue were about 3 times higher than in the liver. That's the opposite of what you'd expect if the sharks had processed the drug recently. It meant the cocaine had been there long enough to store, long enough to accumulate. Their bodies had essentially become filing cabinets. Every swim through contaminated water added a little more. And because sharks live for decades, those files get thick, very thick. The team in Brazil had just opened the first one. The levels were roughly 100 times higher than what researchers had found in previous studies of smaller marine animals. Part of that is biology. Sharks sit at the top of the food web. They eat everything below them. So whatever drugs are swimming around down there eventually end up inside them. But the other part is exposure. The water itself was dirty. Here's what that means in plain terms. Measure the cocaine in one of these sharks the way you'd measure it in a human. The shark would fail the drug test, spectacularly. Obviously, a shark is not a person. The biology is different, the metabolism is different, but the molecule is the same. And that molecule is doing something inside the animal. We just don't fully know what yet. That's one of the quiet parts of this story. The finding came first. The consequences are still being studied. The fish aren't waiting for the paperwork to catch up. The researchers noticed something else. Female sharks had higher concentrations than males. Pregnant sharks had the highest, which means the next generation of these sharks is being born contaminated. They never swim a single meter of clean water. They start with cocaine already in their system. This is where the headline stops being funny. The question of what cocaine does to a developing shark embryo is currently unanswered. Nobody has run those studies yet, but the conditions for those studies are now, unavoidably, in place. The experiment is already happening. We're just not watching it. So there it is, 28 sharks, all positive, high levels, passed to offspring, in an animal that has existed, in its current form, for hundreds of millions of years. But none of this answers the obvious question. Where is the cocaine coming from? Nobody is dumping bags of it into the ocean. Nobody is feeding it to sharks. The drug is arriving through a pathway that is completely legal, technically mundane, and shockingly direct. It does not involve traffickers or smugglers or bad actors. It involves plumbing. Follow a toilet flush and you'll start to see it. Here's what happens when someone uses cocaine. The human body metabolizes about half of it fairly quickly. The rest leaves the body in urine, along with a compound called benzoylecgonine. That's what cocaine becomes after the liver processes it. That urine goes into the sewage system. And the sewage system, in most cities on Earth, was designed in the 19th century. It was designed to carry human waste to a treatment plant. clean it up as much as possible, and release the water back into a river or an ocean. The key phrase being, as much as possible. Wastewater treatment plants were built to remove solid waste, organic matter, and some bacteria. They were not built to remove pharmaceutical molecules. Most of them still aren't. Modern facilities in parts of Europe and North America have added advanced filtration, ozone treatment, activated carbon, membrane filters. These can catch a good percentage of drug compounds, but most of the world does not have those systems. And even the best ones miss a fraction. That fraction, multiplied by a city of 10 million people, is a lot. In some coastal cities, it is a continuous leak that has been running for decades. Think of it like trying to strain coffee through a colander. The grounds stay, the coffee itself passes through. Sewage plants are the colander. Dissolved pharmaceuticals are the coffee. They move straight through the filter, out of the plant, and into whatever body of water the plant drains into. For coastal cities, which is where most humans live, that water goes directly to the ocean. In Rio de Janeiro, the sewage discharge points sit within a few kilometers of the shark habitat that was studied. The pipeline from toilet to shark is shorter than most people would guess. Cocaine is not the only thing getting through. Researchers have identified caffeine, ibuprofen, and acetaminophen in coastal seawater around the world. Also birth control hormones, antidepressants, and antibiotics. Also cholesterol medications and blood pressure drugs. Every medication you've ever taken has a statistical chance of ending up in an ocean somewhere. It's not a dramatic claim. It's a plumbing fact. The drug was designed to be water-soluble so your body could absorb it. That same property is why it doesn't get filtered out on the way back down. The ocean is the world's largest unintentional pharmacy. But cocaine is illegal. Most people flushing cocaine metabolites are doing it passively, through their urine. That accounts for a chunk of what shows up in the water. It doesn't account for all of it. The other source is people flushing actual cocaine, getting rid of evidence before a raid. Panic flushes. Dealers offloading product before arrest. In cities with heavy drug trade, wastewater analysis can reliably detect spikes in cocaine levels on specific nights, Friday and Saturday especially. The sewer, in that sense, knows exactly what kind of weekend the city just had. There's also pharmaceutical manufacturing. In countries like India and parts of Southeast Asia, drug plants sometimes discharge wastewater directly into rivers. Research teams have measured antibiotic concentrations downstream from those plants. The levels are higher than you'd find in a patient's bloodstream. This is not a trickle. This is an industrial leak. Most of those rivers eventually reach the ocean. The drugs travel with them. A molecule made in a factory in Hyderabad can, in theory, reach a shark off the coast of Brazil. Oceans are very large, also very connected. So the pipeline is built. Toilet, sewer, treatment plant, coastal discharge, ocean current. That's how the molecule arrives. But arriving is only the first step. Because once a drug is in the water, it has to find its way into a shark. Sharks don't drink from a tap. They don't have urinary exposure. Something else is carrying the cocaine up the food chain, bite by bite, until it lands in the muscle tissue of an apex predator, decades after the drug left the city. And that something else starts 1,000,000 times smaller than the shark that ends up with the headline. Here's what nobody tells you about ocean pollution. The water itself is usually not the problem. The problem is what lives in the water. Bioaccumulation. That's the word for it. A chemical enters the ecosystem at low concentration. It gets absorbed by the smallest organisms. Those organisms are eaten by slightly larger ones. The chemical concentrates. The larger ones are eaten by even larger ones. It concentrates again. By the time you reach the top of the food chain, the original chemical has multiplied by thousands, sometimes millions of times. The ocean is a magnifying lens pointed at whoever is at the top. Start at the bottom. Plankton. Microscopic plants and animals that form the base of every ocean ecosystem. Plankton do not move much. They drift with the currents. They absorb whatever is dissolved in the water around them, including pharmaceutical molecules. A single plankton carries a tiny amount, far too small to matter on its own, but plankton are everywhere. A cubic meter of seawater can contain millions of them. They are the first absorbers. They are also the first meal for almost everything else that lives in the ocean. The chain officially begins with something you'd need a microscope to see. Next level, small filter-feeding fish, sardines, anchovies, menhaden. These animals eat plankton by the thousands every day. They swim with their mouths open and let the water pass through. Every meal is a low-dose exposure. Over a lifetime, those doses stack up. The drugs don't leave their bodies efficiently. Fat tissue stores them. Liver tissue stores them. By the time a sardine is fully grown, it's carrying a measurable pharmaceutical load. This is not theoretical. Studies have confirmed it in samples from the North Sea, the Mediterranean, and the Atlantic coast of Brazil, and every body of water in between. Up another level, mid-sized predators. Mackerel, tuna fry, squid, rays. These animals eat the small filter feeders, usually a lot of them. Say a sardine carries 1 unit of cocaine. A mackerel eating 1,000 sardines over a season carries 1,000 units. Except the mackerel can't flush it all out either, so most of it stays. The concentration in the mackerel is now significantly higher than in any individual sardine it ate. The ocean is doing math, bad math, in favor of whoever is at the top, and at each step, the multiplier compounds. Top level, apex predators, sharks, large tuna, swordfish, marlins, dolphins, orcas. These animals eat mid-predators, often many of them over a long life. Sharks in particular are extraordinary at accumulating toxins because of 3 things. They live a long time. Many species live 30 to 70 years. They eat a lot. Their metabolism is slow. Whatever they accumulate tends to stay accumulated, which is exactly why the team in Brazil picked sharks to study. If there was pharmaceutical contamination in the ecosystem, sharks would show it clearest and loudest. A shark is a 30-year pollution diary with fins. Let's do the math. Imagine a single plankton carries 1 nanogram of cocaine. A sardine eats 10,000 plankton and carries maybe 8,000 nanograms. Some is lost. A mackerel eats 100 sardines over a month. It carries 600,000 nanograms. A shark eats 1,000 mackerel over a decade. You can finish the sentence yourself. The numbers are illustrative, not exact, but the pattern is real. It is how every major toxin, mercury, DDT, PCBs, has historically made its way up the food chain. Pharmaceuticals are just the newest entry on that very old list. There's one more thing specific to sharks. Cocaine binds well to fatty tissue. Sharks have a lot of fatty tissue, especially in their liver. In some species, the liver makes up 1/4 of their body weight. That liver is a storage vault for anything lipophilic. Lipophilic just means fat-loving. Cocaine is extremely lipophilic. So is DDT. So are dioxins. A shark liver, chemically speaking, is one of the most efficient collection devices nature has ever built. It wasn't designed to collect our pharmacy. It's doing it anyway, and the vault has no exit door. So the pathway is complete. Toilet, sewer, ocean, plankton, sardine, mackerel, shark. Every step is mundane. Every step we've known about for decades. But nobody connected the last link until that team in Brazil ran the numbers. And the moment the study was published, something interesting happened. Other researchers around the world started looking at other animals in other ecosystems. What they found suggests that sharks are not special. Sharks are just the animals we happened to check first. The list of other contaminated species turned out to be much longer than anyone had expected. In 2021, a team of Czech biologists ran a study on brown trout. The river they chose passes through several wastewater discharge points outside Prague. They were testing for methamphetamine. The city has a long-documented meth problem. The drug shows up in sewage at consistent levels. They found it in the fish. Then they ran a behavioral experiment. They gave the fish the choice: water containing meth or water that was clean. The exposed fish had been swimming in meth-contaminated water for weeks. They consistently chose the meth side, every time. Let me say that again so it lands. Trout preferred the water with the drug in it. The Czech team described this as classic addictive behavior. The fish were, by every measurable criterion a neuroscientist would use, addicted to methamphetamine. The problem is not hypothetical. If a fish's central nervous system can become dependent on a pharmaceutical, that is real. A chemical rewiring in an animal that had no choice in the matter. No one prescribed it. No one offered it. The fish just lived somewhere downstream from a city. That was the entire crime. Next example. Antidepressants, specifically fluoxetine, the active ingredient in Prozac. A research team in Portugal exposed wild-caught shrimp to typical coastal wastewater levels. The exposed shrimp started behaving differently. They left the dark areas of the tank, where they would normally hide from predators. They moved into open water. In the wild, that behavior would make them much easier to find and eat. The drug that is used to reduce anxiety in humans was making shrimp lose their survival instincts. The medication worked exactly as designed, just on the wrong species. Then, there are the oysters. Researchers have been monitoring oyster beds near urban outflows for close to a decade. Oysters exposed to SSRIs start releasing their eggs at different times of year. SSRIs are the broader class of drugs that includes Prozac. Their entire reproductive cycle shifts. Oysters rely on synchronized spawning to reproduce successfully. A bed that falls out of sync produces far fewer offspring. Entire generations of shellfish are being rescheduled by prescription medications. Medications that were never meant to reach saltwater. Antidepressants are not just changing individual animals, they are changing the calendar whole ecosystems run on. Dolphins. In 2019, a team in Florida autopsied a group of bottlenose dolphins. The dolphins had died during a harmful algal bloom. They ran pharmaceutical screens on the tissue. They found traces of fentanyl, oxycodone, methamphetamine, and several antidepressants. The drugs didn't kill the dolphins. The algal toxin did that. But the pharmaceutical exposure was real, chronic, and measurable. These were dolphins that had never been near a human medicine cabinet in their lives. They had just been near a coastline. That was enough. The distance from pharmacy to dolphin blood, it turns out, is not very far. Seabirds. A long-running study on herring gulls in the North Sea documented the same thing. Antidepressants, birth control hormones, antibiotics, and anti-inflammatories. In their tissue and in their eggs. The mechanism is the same. They eat fish, fish carry the compounds, the gulls concentrate them further. The birth control hormones are particularly strange. Male fish exposed to high estrogen levels from wastewater have been observed developing female characteristics. In some UK river systems, more than half of the male roachfish show signs of intersex biology. Reproduction itself is being chemically edited by whatever the city is prescribing. There's a pattern here. It's not a coincidence. It's a signature. Pharmaceuticals are doing, at scale, exactly what they were designed to do. They affect behavior. They affect reproduction. They affect brain chemistry and body development. They were designed for human doses in human bodies. They are now being delivered in wild doses to wild bodies. Bodies that have no medical reason to be exposed. The effects are predictable because the drugs work. That is the uncomfortable part. They wouldn't be affecting ocean life if they weren't effective medicine. But they are. And they are. And nothing about that contradiction is going away. Here's the question every marine biologist running these studies ends up asking. Should the company that manufactures a drug be responsible for what happens after the patient excretes it? Legally, the answer right now is no. The moment a pill leaves the factory and is sold to a person, the company's liability ends. Everything that happens downstream, literally downstream, is somebody else's problem. Usually nobody's. That liability gap is where the entire ocean is sitting. Nobody owns the problem, which means nobody is obligated to solve it. And so far, nobody has. Let's pause and steelman the other side. There is a version of this story that goes too far. And the fastest way to lose credibility is to pretend there is no counter-argument. There are real scientists who think the cocaine shark finding, while technically true, is being dramatically overplayed. They have good reasons. They are worth hearing out. Here are the 3 strongest objections to everything said so far. Each of them lands a real punch. None of them, in the end, quite knocks the story down. Objection 1. The concentrations are low. Nanograms per gram of tissue. Billionths of a gram. Compared to the amount a human uses recreationally, these quantities are tiny. Too small, they argue, to have any effect on an animal as large as a shark. This is true, partly, but the argument assumes that dose-response relationships in humans translate directly to marine animals. They don't. Fish and shark physiology is different. Some drugs are more potent in cold-blooded animals. Some are less. Nobody has mapped the differences yet. Low dose in a human is not automatically low dose in a shark. Objection 2. Sharks have robust detoxification systems. They have been filtering heavy metals, marine biotoxins, and environmental poisons for over 400 million years. The argument is that they can probably handle trace pharmaceuticals too. The cocaine in their tissue, they say, is not doing meaningful damage. This is also partly true. Sharks do have impressive detoxification biology. But the Brazilian study found something different. The concentrations were increasing with body fat, increasing with age. Highest in pregnant females. Whatever the detox system is doing, it is losing ground over time. You don't accumulate something you're successfully clearing. Objection 3. Media sensationalism. The phrase cocaine shark is irresistible clickbait. It drives social shares. It drives outrage. It drives headlines. The concern, reasonably, is that the real science is being flattened into a meme. The actual finding is complex. A chronic low-dose exposure pattern in multiple species. That gets replaced, in the public mind, by a cartoon shark doing lines off a surfboard. This is completely true. The coverage has been bad. The science has been good. Those two things are both allowed to exist at the same time. One does not invalidate the other. But none of these objections changes the underlying finding. The drugs are there. They are bioaccumulating. The exposure is chronic. The delivery pathway is fully understood. And the same pattern has been replicated with other pharmaceuticals, in other species, across multiple oceans, by independent research teams. The skeptic's strongest argument, in the end, is that we don't yet know exactly how harmful this is. That's fair. It's also not reassuring. It's just saying the study hasn't finished. The contamination, meanwhile, is not waiting for the study. It's running faster than the science can track. Now, the reframe. Because the reason this story matters is not that sharks are doing coke. It is that sharks are on our dinner plates. Not Brazilian sharpnose sharks specifically, though they are eaten in parts of South America, but sharks in general. Globally, humans consume an estimated 100 million sharks per year. Most of that is shark fin. Some of it is shark meat. Much of it is mislabeled as other fish at markets. Mako, dogfish, and spiny shark often show up under the names sea bass, smoked fish, or simply whitefish. You have probably eaten shark, you just didn't know. Now expand that. Humans also eat tuna, swordfish, salmon, cod, tilapia, shrimp, oysters. Every single animal discussed so far in this episode is in the human food chain. Global seafood consumption is at an all-time high, over 160 million tons per year and rising. The World Health Organization recommends fish as a healthy protein source. For protein density and omega-3 fats, that recommendation is completely accurate. But the same organization that recommends fish has also been tracking pharmaceutical contamination in fish. Those two tracks do not meet in public conversation very often. The bioaccumulation pattern that moved cocaine from plankton to shark does not magically stop at the shark. A predator that eats a contaminated shark inherits the concentration, whether that predator is another shark, or a killer whale, or a human. Researchers have documented this with mercury for decades. Pregnant women are told to limit tuna for a reason. Tuna has accumulated huge amounts of mercury from the fish it ate. Eating it transfers a measurable dose straight into the human bloodstream. Mercury is just one molecule. There are hundreds of pharmaceutical compounds doing the same thing at the same time, right now. And the human body itself has been tested. Not for cocaine specifically. That's complicated. People who test positive for cocaine are usually already under suspicion for using it. But for antibiotics, painkillers, caffeine metabolites, and industrial chemicals from pharmaceutical manufacturing, these have been found in human blood samples in every country studied. A recent monitoring program in the European Union tested the blood of people who had taken no medication. Measurable levels of pharmaceutical compounds came back. The source was diet, specifically fish. The loop, in other words, has already closed. This is structurally identical to the microplastic story. A few years ago, the idea that microscopic plastic particles were circulating inside human bodies sounded like fringe science. Then the research caught up. Now we know microplastics are in human blood, human lungs, human placentas, and human breast milk. The source, ocean plastic entering the food chain, concentrating up through predators, ending in us. The pharmaceutical story is running a decade behind the microplastic story. Same pipeline, same mechanism, same destination, just a different molecule. The outcome is not going to be different. Food chain physics does not negotiate. Solutions have been attempted. The European Union passed a Water Framework Directive in 2000. It listed pharmaceutical pollutants as priority substances for monitoring. Germany, Switzerland, and the Netherlands have upgraded wastewater plants. Ozone and activated carbon filtration. These plants can remove over 90% of pharmaceutical residues. The technology works. It is also expensive. A single plant upgrade can cost hundreds of millions of dollars. Most countries have not done it. Most cities never will. The ones that have still only treat a fraction of the total sewage flow reaching their coasts. The rest continues to pass through unfiltered. The alternative? The approach taken by a few forward-looking municipalities is called source control. Don't let the drugs enter the sewer in the first place. Pharmacy take-back programs, public education campaigns, unused medication drop-off points. These programs work, measurably, but at a small scale. They can reduce pharmaceutical input by perhaps 15 to 20%. Only in cities that use them aggressively. Not enough to matter globally. not anywhere close to what's needed to meaningfully lower ocean concentrations. The scale of the problem is bigger than the tools currently being used against it, and the gap is widening, not closing. So what are we left with? A drug pipeline that leaks by design, a food chain that concentrates everything, an apex predator carrying pharmaceuticals from 100 different cities, a dinner plate at the end of it, and a policy system that is not caught up to the science, is not catching up, shows no urgent signs of intending to. The cocaine shark headline wasn't wrong, it was just too small. The actual story is bigger than any one drug, any one animal, any one ocean, and it has already arrived inside the people reading it. Here is the verdict. The sharks are not addicts. They are archives. Every swim of every day, they have been filing away what the cities above them have flushed down. Cocaine, caffeine, painkillers, antidepressants, all of it. Not because they are special, because they are downstream. And downstream, eventually, catches up to upstream. That is not an environmental claim. It is a geometric one. Water moves in one direction. So does whatever is dissolved in it. The ocean is not a drain. It is a ledger. The thing about a food chain is that it does not care where you are on it. It just moves the molecule forward. Plankton do not know they are carrying cocaine. Sardines do not know they are passing it on. Sharks do not know they have stored 30 years of somebody else's weekends inside their liver. And the person at the fish market buying swordfish for Friday dinner cannot see it either. No way to see what trip the molecule has been on to reach them. The ignorance is universal. The contamination is not. One of them is spread evenly. The other is not. What makes this different from mercury or DDT is the pace. Mercury has been in the ocean for hundreds of years. From mining, from coal, from natural volcanic sources. DDT was a mid-20th century chemical, eventually banned in most countries. Both were bad. Both were eventually regulated. Pharmaceuticals are new. Synthetic compounds at planetary scale are a development of the last 70 years. The ocean is still absorbing the first wave. The second wave has not even landed yet. Everything currently being prescribed, every new drug in every pharmacy pipeline. What we are measuring now is already history. And there is one detail that has been sitting quietly in this story the whole time. The Brazilian team tested for cocaine because it was easy to measure and impossible to deny. The researchers have said in later interviews that they chose it partly because nobody could accuse them of exaggerating. A positive test is a positive test, but the same sharks in the same tissue were carrying a dozen other substances, painkillers, stimulants, antidepressants, antibiotics, all at similar levels. Cocaine was the headline. It was never the point. The point was everything else that came with it. The drug was the messenger. The sharks will keep swimming. The cities will keep flushing. The chain will keep doing its math. And somewhere in a coastal current right now, a plankton is absorbing a molecule that started its life in a laboratory, passed through a person, now at the beginning of a decades-long journey toward a dinner plate. The headline made us laugh. The laugh is the part we'll remember. The rest, we probably won't. At least not until it reaches us, and it is already reaching us. The ocean does not have a disposal system. Everything we have ever put into it is still there, just moved. Subscribe if you want more stories like this. What would you pay to clean the pipeline? Tell me below. This is Curious Minds. See you next time.